All right, let's go ahead and get started. The midterms, as some people can see up here, everything is actually in alphabetical order, so hopefully you're doing a binary search through only one file and not a linear search through all five. But they'll be up here after class. I don't have distribution information on the website yet because I didn't have time to put that information on the website before class. But at a very high level, the mean was about half a point higher and the standard deviation was about 2 points lower, which means actually quite surprising to me. I expected the average to be somewhere in the low 20s. People did better, and moreover, the distribution is narrower, so it's not just people did better but more spread out, but basically the bottom of the curve went up. So as I said, we'll post the actual list of numbers with corresponding grade, letter grades, and I'll actually post sort of summary distributions for the two midterms put together, so people have a reasonable idea of where they stand going into the final exam. The last homework, I don't know if I mentioned this last time, hopefully everybody's noticed. Homework 10 is out, it's due next Tuesday. This is going to be the last homework that we can promise to grade. Homework 11 will be out, either next Monday or Tuesday, and it'll be due 1 week later, in the sense that Tuesday evening or roughly we will post solutions, but there won't actually be a submission site because 1 week later is the last day of class. Okay. So because we're coming up on the very end, let me actually give you the calendar from here on here to the end of the semester. Okay, so this is where we are today. We're going to start talking about approximation algorithms today. Homework 10 will be due next Tuesday, and homework 11 will come out. This is the last day of class, and the final exam is that Friday. So today is the 21st, 19 is the 26th, 27, 28, there's class. On the 28th, at the end of class, I will distribute ISIS forms. The last day of class will be entirely, do you have any questions for me? And this is not intended to be solely a review session for the final. I am going to, I believe Thursday is reading day. I'm going to try to set up a review session sometime on Thursday. This may be a bit of a challenge because I imagine everybody's going to be trying to set up a review session on Thursday. Of course, this will be recorded and the video will be available and the notes will be available as soon as the review session is over. The final exam starts at 7 p.m. It's late on Friday. There'll be a form for you to sign if you, for some reason, need to take a conflict exam. I know there are a couple of people who are taking both this class and applied machine learning, for example. The way that final exams are scheduled is that they're scheduled according to when the actual classes meet. So there will be a conflict exam, hopefully relatively early the following week. Let's see, what is this? 28, 29, 30. January, February, March, April, 31, 2, 4, 5. I believe the Friday, May 5th will be the final exam. So we're in the home stretch. There are only going to be 3 more real lectures, including today's real lecture. Homework 11 will contain some material from the lecture today and Tuesday, which will show up on homework 11 and may show up on the final exam. So you should think of homework 11 as a set of practice problems, possibly leading into the final, but there simply isn't time between the Tuesday that it would be due to get it back to you before the final exam. So we're not actually expecting to grade it, and that also necessarily influences the difficulty of the problems that we can ask about the last bit of course material. Okay, so I'll repeat this calendar as we count down to the end of the semester. Any other administrative questions? Okay. Someone pointed out to me that yesterday that everyone who took 374 either last semester or the semester before saw problem 1 on the current homework in the headbanging session. So make sure you actually understand how it works. Don't just dig out your old notes or talk to somebody who was in 374 last semester, transcribe it down, actually figure out how it works. Okay. So the last several lectures we've been talking about problems that are hard. And most of the time we've been talking about problems that are NPhard, meaning no polynomial time algorithm, unless a miracle occurs. That miracle would be known as a proof that P equals NP. Nobody believes that's going to happen. And then earlier this week, we talked about, ETH and SETH, which basically mean no sub-exponential time algorithms, subject to the assumption that 3SAT doesn't have any sub-exponential time algorithms. And SAT, in fact, implies not only are there no sub-exponential time algorithms, but there are no exponential time algorithms where the base of the exponent is less than what you would get from absolute brute force, at least for CNF SAT. And there's a bunch of other things like consequences of SAT that I briefly alluded to at the end of the lecture on Tuesday that say, for example, there's no subquadratic algorithm for longest common subsequence. Right? So there are problems where we can solve them in polynomial time, but the polynomial might be so large that for the kinds of problems that we're interested in solving, even quadratic time is too much. So longest common subsequence and edit distance, which we saw earlier in the semester, are good examples of this, where if you're trying to do a comparison between two human genomes, so this is on the order of a few billion base pairs. Base pairs are letters from a 4-letter alphabet, A, G, C, and T, but they come in pairs. A matches with T and G matches with C. So just think of them as symbols. The human genome is about 3 billion symbols, about 6 billion bits, if you want to think of it that way. So running a quadratic time algorithm to compute the edit distance between my genome and your genome is just going to take too long. Okay. And if you want to do something even more more convoluted, like let's take everybody's genome in this room and try to see if there's a way to get a consensus genome, a string that is closest in edit distance to everybody in this room. This is a perfectly reasonable problem, and given that there are about 50 people in this room, there's a polynomial time algorithm to do it, but the exponent of the polynomial is 50. Because it's this 50-dimensional dynamic programming problem. There's no way to actually do that in real life. And there are ETH and Ceph-based lower bounds that imply unless Ceph is false, you actually can't do any better than that. Right? So there really are fairly natural problems where the best algorithm we know is exponential, and there's good reason to believe why you can't do much better than that, or the best algorithm is polynomial, but the polynomial is too big to reasonably run on large data sets, and there are good reasons to believe you can't do better than that. So what do we do? There are literally thousands of problems in the category of being NP-hard. There are literally, I don't know if I want to say thousands, but there's a reasonable guess that almost any problem that you can solve with dynamic programming falls into the second category of the dynamic programming algorithm. You're not going to be able to do much better than. And so if it, unless there's some like monotonicity or mon structure under the hood. So what do? Well, you have to solve these problems anyway in the real world. Which means we're kind of forced to back away from one of the bedrock assumptions that we make when we design and think about the efficiency of algorithms. So one of those assumptions is the algorithm must work for all possible inputs. Right? We talk about worst case behavior of an algorithm, and we imagine an all-powerful, all-knowing malicious adversary that designs the input precisely for the purpose of making our algorithm slow. But as several people have observed, thinking about these NP-hard problems, there are special cases of hard problems that are easy. So it's possible that you can exploit some structure in the actual input. And this is actually, I think, the much more common approach that people take from a practical standpoint. From a theoretical standpoint, this is a little bit uncomfortable because it requires actually assuming a particular structure in the input. Now that assumption may be borne out by some experimental analysis of the kind of data that people actually work on. So a good example of this is the kinds of clustering problems that you generally run into in machine learning applications. There's a standard algorithm for clustering called k-means, which is known in the worst case to require exponential time. But in practice, it works great. And the reason why k-means works great as a clustering algorithm, when it does, is that provably, if the data is nicely clustered to begin with, and there's a formal way of stating this, if you can assume I generated the data in k clusters, and then I fed it to k-means, k-means will recover those k clusters very quickly. Provably, in polynomial time, near linear time, with the right definition of what a clustering is. So if we think about the behavior in the worst case, this is a horrible algorithm. But if we make an arguably realistic assumption that we're only actually going to be interested in clustering data when the clustering makes sense, so the data can be clustered, then with that assumption, we can impose some explicit structure on the input that allows us to refine the analysis of the algorithm to show that it actually runs quickly. Okay. This is largely domain specific. Different problem domains, different applications categories will want to make different assumptions about what the structure of the input looks like. It's a little bit hard to talk about generalities in a class like this. So there's a different approach, which is much more commonly taken by theoreticians than practitioners, but nevertheless is informative because in practice you can actually do both. And the second thing is back away from the assumption that what we want is the best possible solution. Instead of saying, I want the absolute best, I want the exact edit distance, I want the absolute minimum number of operations I need to get from string A to string B. Or I want the absolute shortest traveling salesman tour. Or I want the absolute minimum number of colors to color the vertices of this graph. And say, okay, the best is the enemy of the good. I don't necessarily want something optimal. But nevertheless, I want something provably good. Okay, so instead of optimal solutions, compute provably good solutions. Now, of course, this requires a definition. What does good mean? And the definition that I want to talk about today is it's close to optimal. Okay, so it'd be nice to be able to say, I don't know whether this is the absolute correct answer or not, but I can guarantee that it's within 5% of the correct answer. Okay. So before I talk about, in more generality what good means, let me just say what these are called approximation algorithms. The idea is that I want to compute a solution that provably approximates the optimal solution within some error tolerance. Okay. So I'm going to start with an example from scheduling. Okay. So I want you to imagine that you have m different machines, which are, for purposes of this problem, all identical, and I have n jobs which I need to run, which for purposes of this problem are just lengths of time. And I need to distribute these jobs to the various machines. And intuitively, what I'd like to do is get all of the jobs done as quickly as possible. Okay, so I have n jobs. And I'm going to imagine that really what I'm given is the running times of these jobs in an array. Now, those of you who do systems for a living should already be snickering. How do I know the running time of the job in advance? You don't. This is an abstraction of a real scheduling problem. And I have m machines, which I imagine to be identical. And I want to assign each of my jobs to a machine. And then after the assignment is done, each machine will execute its assigned jobs serially, one at a time, until it's done. Okay, so I want to compute an assignment, which I'm going to write as, let's just write it this way, 1 through n, where I'm going to run job I, sorry, maybe I should, let's call this run job I on machine M sub I. And what I want to do is minimize the max over all machines I, the sum over all jobs J such that the machine that job J runs on, it happens to be I, of the running time for job J. So let me change this. This job J runs on machine M sub J. Okay? Now, if you saw this problem for the very first time, how would you think you might actually solve it? Yeah? There was a question?
I don't understand the notation. Why do you like max y and then sum?
Oh, I'm sorry. That max should be a min. I'm sorry. I want to minimize the completion time. So this is the minimum over all machines.
It should be max. It should be max.
It should be max. Oh, you're okay. Fine. Ding, 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 ding. Undo. Okay. I want to minimize the total running time of all jobs assigned to the worst machine. So I is the identifier of the machine. This is the total amount of time that machine I will run because it's executing jobs. So I take the max over all machines, and then that is the function that I want to minimize. So there's a reasonable picture that you can imagine here. If by thinking of the machines as bins and the jobs as boxes. So I'm going to put one box here, and I'm going to put another box here, and I'm going to put another box here. And the idea is that I want to arrange the boxes so that what's called the make span, which is the height of the tallest stack, is as small as possible. Okay, so there's a word on the screen. I'll give you a hint. It's misspelled. That should suggest a way of solving this problem. Yeah? Assignment. See that? It's misspelled. I'm assigning jobs to machines. I should set up a bipartite graph where the machines are on one side, the jobs are on the other, and I want to compute some minimum cost matching. All I have to do is figure out, oh God, that objective function isn't linear. Crap. No, this is not going to work. This problem is NPhard. So there's a proof that works from the partition problem, which is one of the problems that unfortunately we didn't have time to actually talk about. This is, given a set of integers, is it possible to split it into two sets whose sums are exactly the same? Now, this is essentially the same as the scheduling problem I'm looking at here when the number of machines is exactly 2. If I have exactly 2 machines, the best I could possibly hope for is to split my jobs into 2 sets, one for machine 1 and one for machine 2, that finish at the same time. Because if they don't finish at the same time, one of them is going to finish later. If I'm even a little bit more careful, I can do an NP hardness from 3 partition, which if you hopefully remember, this is not partitioned into 3 things, but rather partitioned into sets of size 3, where I want all of the sets to be the same. So in this case, the hardness reduction says, I'm given this set bag of numbers, I want to split into 3s. Essentially what I do is I set up, I make the number of machines equal to the number of numbers over 3. I add some constant to every number to avoid some cases. And then I want the stacks to all line up. And the only way to do that is to have exactly 3 jobs in every machine. There is a dynamic programming algorithm that can solve this problem, provided the make span M is small. What's the dynamic programming algorithm's running time? Okay, yeah, it's n times capital M to the M. So you need a table where the dimension of the table, the number of axes, is equal to the number of machines, and the width of the table in each of those directions is the make span that you're trying to compute. If you're wondering, this is exponential because this make span might require the number of bits I might need to write this down might be exponential in the size of the running times I've given as input. Right, the number of bits I need to write M could in fact be exponential in the number of bits I need to write down that array, T.
Also the lowercase m.
Well, also lowercase m. True, but this is going to be dominated by n. Yeah?
Is there a integer programming?
There is. Right, because integer programming is NPhard. Right. We'll talk about integer programming a bit next week. Okay, so the right way to say this is there is an integer programming formulation of the problem, is there a schedule with make span less than some target value M? And then you could do a binary search of the possible values of that. But still, that particular integer programming problem is NP-hard. Okay. All right, so forget the NP-hardness. Forget the dynamic programming algorithm. You don't really don't want to be running that dynamic programming algorithm. How would you solve this problem? Right? If you just saw this before you took 473, what would you do? Yeah.
Schedule the big ones first, and each one schedule goes in the bin with the fewest things in it.
Okay, so the suggestion is to do two things, right? The first thing I'm going to do is sort the jobs, which rarely means sort the running times, in decreasing order. So I'm going to consider the jobs one at a time. I'm giving them all in advance, which is also a little bit weird as a scheduling problem, but okay. I'm going to consider the big jobs first and the little jobs later. Anyone who has ever moved apartments or packed a car or packed a suitcase to go live in a foreign country for 9 months. Big suggestion. Pack the big stuff first and then pack the little stuff around it. Don't pack little things and then expect to be able to put your TV in at the end. Right. So this is just a general, for some reason what people call a life hack. Do the big stuff first. And the second one is that I'm going to consider the jobs one at a time. But let me be consistent and always refer to jobs by the letter J. Put job J into the bin. Well, let me, instead of saying putting in the largest bin, I know it's the same problem. Assign job J to the machine that would finish first. So far. Okay, so at the beginning, I take the largest job and I assign it to any machine, because at the beginning of time, each machine says, I'll be done at time 0. So you just break ties arbitrarily. And then you take the second largest job and you put it somewhere that still says 0. So the first M jobs are pretty simple. You just assign them to the M machines. And then after that, you take the next one and you say, okay, which one of you can take this first? And that's the machine that you give the job to. So it turns out that this algorithm is guaranteed to compute a solution where the make span is at most 4/3 times the optimum make span. So it's at most 33% larger than optimal. Now I'm not actually going to prove 4/3. That requires a bit of a few more details that I'm prepared to actually do right now. I'm going to actually prove, an upper bound of 3/2. I'll convince you that I'll try to convince you that this greedy algorithm is at most 50% worse than optimum. But before I even do that, I'm going to prove something even simpler, which is that this is at most twice the make span of this greedy schedule is at most twice the optimum. And this is what I mean. This is the kind of thing that I want to say when I'm talking about an approximation algorithm. I take the performance, now not measured in terms of running time, but in terms of the resource that I'm trying to optimize, in this case, make span. And I say I can compare the make span computed by my algorithm to some optimal algorithm, and I don't know what the optimum algorithm is. I don't care, in fact, what the optimum algorithm is. I wouldn't want to run the optimum algorithm even if I knew what it was, because the problem is NPhard. But nonetheless, I can guarantee that the make span that my algorithm computes is not too much bigger than the optimum make span. Okay. So, and in fact, for proving this approximation ratio of 2, I'm for the moment going to ignore step 1 here. I'm not going to sort the jobs because I don't need to sort the jobs in order to get an approximation ratio of 2. And just the jobs come in whatever the order they are, and I do sort of the obvious things. You give me a job, I put it on the machine that will finish first without, if we had stopped just now. Which machine is going to finish first? Okay, you get job J. That's it. So the way I'm going to do that is the following. Let me suppose that I'm going to pick out machine I. Machine I is the one that determines the make span. And I'm going to pick out a particular job J. Job J is the last job executed by machine I. Okay, so this is, if you think of this as a pile of boxes, box J is the one whose top is furthest up. Okay. And now I want to split the make span, which I started by saying, okay, here's time 0, here's time m. Let me split the make span here at m minus t, the running time of job J. What I want to claim is, let me erase this. It's not actually that interesting. What I want to claim is that this vertical distance, that amount of time, is less than or equal to the optimal make span. And this amount of time is also less than or equal to the optimum make span. Okay? So, claim. The make span computed by this algorithm is at most 2 times opt. Okay, so proof. Sort of machine I ends last. This is the definition of I. Job J ends last. This is a definition of J. Okay, so there are two things that I want to consider. The running time of job J and the overall make span minus the running time of job J. Okay, so the first thing I want to do is I want to claim that the running time of job J is less than or equal to the optimum make span. Can anyone give me the one-line proof?
In the optimal schedule, that job has to be done by a machine.
Yeah, you have to run job J. It takes that much time. Whatever machine runs job J is going to end on or after time t of j. So in particular, whatever machine ends last, it's going to end, the ending time is going to be greater than or equal to this. And it doesn't matter what the schedule is. In every schedule, the make span is greater than or equal to t of j. So in particular, opt is the best possible make span is greater than or equal to t of j. Okay? All right, well, that was pretty easy. Okay. So what else do I want to say here? Somehow I need to come up with another way of proving something about this quantity, m minus t of j. So let me look at before I go directly into this, maybe another thing I should point out here is the strategy that we're using here to try to prove this upper bound on the make span of the optimal algorithm is to really think of it as I'm trying to prove a lower bound on optimum. I'm trying to prove that optimum is greater than or equal to something which I eventually will put together to get make span. So are there any things that, I can show optimum is bigger than? I showed it's bigger than the running time of job J. Are there any other things that I can show that optimum is bigger than?
Sum of the running time divided by the number of machines.
Okay, so this is, I can take the running time of all the jobs and divide it by m. So this is the make span that you would get if you could subdivide jobs and split subjobs up, fractional jobs up among the machines. If jobs were water that you could pour some of into one machine and some of into another, you could arrange for the top of the schedule to be exactly even because every stack was exactly the same height. The sum of all the heights of the stacks is just the total running time of all the jobs. And so then divide that by the machine. Okay. So, okay, this is a good kind of lower bound. There's another one which we sort of used implicitly, which is the optimum is bigger than the running time of every job, not just this one particular J that I picked out over there on the left. In particular, the optimum is bigger than the running time of the longest job, which may or may not be job J. All right. So, at some point I have to actually look at the algorithm and ask, I haven't referred to the rule that I've used to assign jobs yet. That might be a sign that that's something I need to think about. Otherwise, I'm not really arguing about this algorithm. I'm arguing about any schedule. And so we can ask, why was job J assigned to machine I? The reason that job J was assigned to machine I was that at the time that job J was assigned, this was actually the shortest stack. Not the tallest, which it is now at the end. But this was the shortest stack when it was slide. That's why we put it there. And now, there are other jobs in here that might have come in after J, but those later jobs will only make the other stacks bigger. So what I can conclude from this is that if I remove job J, that this stack that shows me the schedule for machine I should be the shortest of all of the stacks that are left, which is in fact the case here. All right, so let me say that again. If I remove job J from the current schedule, then machine I, instead of being the last machine to finish, will become the first machine to finish. Otherwise, I would have put job J somewhere else. Okay? So, what does that say about the make span minus T of J? This is smaller than the total running time. Sorry. For any machine. I mean, it's obviously shorter than the total running time for machine I, because N is the running time. But it's less than the total running time for any other machine also. Now, I'm almost done. Is there anything anything else I might be able to compare this to? Let me say just any single machine. All the pieces are actually on the screen at this point. We just need to put the last two notches and tab A to slot B to finish the proof. Yeah.
Well, it's that thing on the bottom left is less than or equal to the thing on the up right.
Here.
Yeah.
This is the average finishing time of all the machines. But this is less than the minimum finishing time of all. It's actually equal to the minimum finishing time of all machines. The minimum is always less than or equal to the average. Okay. So in particular, M minus T of J is less than or equal to the minimum over all machines I prime of the total running time on machine I prime. This is less than or equal to the average of the total running time on 1 over m times the sum, but that's just this, so this is less than or equal to opt. Okay. So I've shown that Tj is less than opt, less than or equal to opt. And I've shown that M minus T of J is less than or equal to opt. And so my conclusion is that the make span computed by this algorithm is at most 2 times opt. Okay? Everyone trying to get the idea behind the game that we're playing here. At some level, what I'm doing here is I'm kind of not really thinking about the make span computed by the algorithm directly at all. And I'm not thinking about the make span of the optimal solution directly at all. What I'm actually doing is I'm saying, well, here's my make span. And this is less than 2 things which I'll call x and y. And I'll show that x is less than or equal to opt, and I'll show that y is less than or equal to opt. Right? This is the core of the argument. And the trick is to figure out these intermediate things, x and y. The first one we chose is well, the running time of whichever job finishes last, and the other one was the make span minus x, basically. And so this is the art of doing the analysis of an approximation algorithm, is I need to choose something that gives me a lower bound on the performance of the optimal solution, while simultaneously giving me an upper bound on the performance of the algorithm I care about. Right. Okay. So I actually promised earlier that I was going to prove not just a factor of 2, but a factor of 3/2. The factor 2, by the way, is the best that you can hope for that particular algorithm. Yes?
So did you essentially say m minus t of j plus t of j is less than equal to alpha plus alpha?
Yes, that's right. So the final puzzle pieces are, I take these two things in the green boxes and I just sum them up. Yeah. I'm sorry.
Can you make that argument again? Where you say that it's total time for any single machine?
Okay, so the question is, can I repeat this argument? This is the place where I say, why is this? Because this is what the algorithm says that I have to do. Why did I put job J assign it to this machine? Because this was the machine that at the jth iteration of my algorithm, when I assigned the job, this was the machine that had the smallest finishing time. Now let me put my hand on the finishing time before I assign job J. All the other machines have later finishing times. And I continue assigning jobs to those later machines. So their finishing times keep getting later.
But when you remove this job j,
Yeah?
when this machine I iteration, you will put the now whatever your j.
Oh no. So let me say this carefully. I don't mean if I throw job J out the window and recompute the schedule. What I mean is if I compute the schedule and then throw away job J. Yeah. So all of the other stacks are taller than the bottom of box J. Is really all this is saying. Because that was true when I put box J on the pile. Okay. So let me try to convince you that this bound of 3/2 instead of so I'm going to claim this now for the algorithm where I really do need to use the fact that I sorted the jobs from largest to smallest. So let's see, how does this actually work? Well, again, I'm going to say machine I finishes last. This is a definition of I. And job J finishes last. This is the definition of J. Okay, good. I didn't want that. All right. All right. So there's actually a couple of cases to think about. One is if there's only one job assigned to machine I. All right, so in this case, the schedule looks something like this. There's right? So job J is in fact the only job assigned to machine I. What can I say about the schedule in this case? It's optimal. Why is it optimal?
You have to keep it somewhat easy.
Right. So if you remember earlier in the previous proof, we said, oh, opt has to be bigger than T of J, and it actually doesn't matter what which J we pick. The opt has to be the optimal make span has to be larger than the running time of any particular job, in particular that one. On the other hand, the make span of this particular job is T of J, because that's the job that finishes last. But by definition of optimum, M has to be greater than or equal to opt. Right? Optimum is the minimum possible make span, so it could be M or it could be smaller, but it can't be bigger. And if I put these three inequalities together, I end up showing that all these three things are equal. Okay? So in this particular case, I actually have M is equal to opt. The schedule is in fact optimal, and so I don't have to think about this case anymore. I've proved the claim for this particular case by proving something stronger. Okay. So otherwise, there is more than one job assigned to machine I. In this case, then, I claim that J must be larger than M. Why is that? So M, remember, is the number of machines. So in this case, what my schedule looks like is something like this. Here's job J. This is the one that finishes last, and it's not the only job assigned to machine I. Why can't job J be one of the first M jobs? Yeah. Sorry? Well, yeah, that's right. But why? You just spelled it out. Because I think not everybody sees it. So the first M jobs go into machines 1, then 2, then 3, then 4, then 5. Just the first M jobs get assigned to each of the M machines because of the way the algorithm behaves. The algorithm always assigns the job to the next machine that has the lowest finishing time. So until we've assigned the first M jobs, at least one machine has a finishing time of 0, and that's the one that's going to be assigned. So I can, in fact, without loss of generality, assume that the first M machines, the first M jobs, job J is assigned to machine J, just as a for loop. Okay. So if J is not the first job executed by a machine, it can't be one of the first M jobs that need to be scheduled. Okay, so this is again because of the way the algorithm works. But this now means that T of J is smaller than T of 1 up through T of M, again because of the way the algorithm works, in particular because of step 1 of the algorithm. This is the first place where we've used the fact that the jobs are sorted from longest to smallest. This is longest to shortest. Okay? All right. So let me actually write this instead of saying j is at least m, let me actually write j is greater than or equal to m plus 1. Okay, so let me think about the way that the scheduling algorithm behaves on these first m plus 1 things. The first m plus 1 jobs might include job j or it might not. So if I just think about the first m plus 1 jobs, what is that schedule going to look like? Let's assume that I'm always going to put, if there's a tie, I'm always going to break by going to the left. So where's job 1 going to go? First machine. Where's job 2 going to go? Where is job 3? Okay, good. Notice they're getting smaller. And eventually job M goes into machine M. Where does job M plus 1 go? It also goes into machine M. Okay, so this is job M, and this is job M plus 1. Okay? Now, what can we say about T of M plus T of M plus 1? This makes span so far. Yeah, this is less than or equal to opt. Not because these two machines have to be scheduled on the same machine, but because among these m plus 1 jobs, some pair of jobs has to be scheduled on the same machine. Some machine has to execute at least 2 of these m plus 1 jobs. And this is the smallest make span I could get by executing 2 jobs. Okay. Good. But now, what does that say about T of M plus 1? It's less than half of opt. Actually, should I say is this T of M? No, sorry. I really meant T of M. The smaller of these two, which is T of M, this is something, sorry. You're right, sorry. Off by handedness. There's a larger job and a smaller job that sum up to something less than opt. So their average must be less than half of opt. So their minimum must be less than or equal to half of opt. But wait a minute. T of j, because j happens after the first 10 jobs, must be less than or equal to T of M plus 1. And so now what I've done is I've taken the first trivial part of the analysis of the algorithm when we didn't sort. It just said T of j has to be less than opt. And concluded that in fact, in the case that I care about, T of j has to be less than half of opt. Right? And so I've already concluded that m minus T of j is less than or equal to opt. That we proved that before. The earlier analysis still holds, and so I conclude that m is less than 3/2 of opt. And again, I'm just adding up this inequality and this inequality to get that. Okay? So with a little bit more work, with a little bit more case analysis, you can actually speed up, you can improve the analysis even further. You can show that in fact there's an approximation ratio of 4/3. But I want to talk about a different problem. And the secret to getting the better approximation algorithm is splitting the analysis into more cases, and for each case, finding the right thing that looks like X and Y in the original analysis. finding the right thing that fits in between the make span of the algorithm that you're having, your greedy algorithm, and the make span of the optimal algorithm. And 4/3 actually turns out to be the right answer in this case. Okay. All right. So let me switch gears, unless there are any other questions about scheduling. If you do any sort of systems work, you will run into a scheduling problem. It will not be this one. There are hundreds of people that work in scheduling, and if you put any 50 of them in the room and say, tell me your favorite scheduling problems, you'll get 102 different answers. Everybody comes up with their own scheduling problem. All of them are NP-hard. Some of them have simple approximation algorithms, and most of them don't. There are some problems where even computing an approximate solution is NP-hard, and scheduling often falls into that category. But this is a reasonably simple one where the obvious algorithm is actually pretty good. Okay, so I'm going to talk about another NP-hard problem where there is an obvious algorithm and it turns out to be pretty good. And so if you remember the vertex cover problem, you're given a graph and you want to find the minimum number of vertices that cover every edge. And, okay, so this is a vertex cover. I have no idea whether it's minimum or not. I think it's almost certainly not. So I want to find the minimum number of vertices that cover every edge. Now this is one of the problems that we showed at the last week. This is NP-hard. The NP hardness follows directly from 3-sat. The exponential time hypothesis implies there's no sub-exponential algorithm for this problem. Yeah.
Since the scheduling problem is NP-hard, if you have a polynomial time reduction of another NP-hard problem to the scheduling algorithm, you have a decent approximation that.
Okay. So this is an excellent question. Do reductions preserve approximation? The answer is no, and the answer is no for, again, a subtlety about the way that we prove things are hard. The way that you prove that something is hard is you take a known hard problem and you solve it by reducing it to the problem that you care about, and saying, oh, but that's impossible because I know that the larger problem doesn't have a polynomial time solution. So I derive an algorithm for 3-sat from an algorithm for vertex cover. Example. So you can say, oh, well, I've got an algorithm for vertex cover sitting right there. What if I plug in an approximation algorithm for vertex cover? Would that give me an approximation algorithm for 3-sat? Well, it depends on how the reduction works. If the reduction works by the inner algorithm computes a number and you just spit it out as the solution to the outer algorithm, then yeah, you'll still get the same approximation. But if you remember, the way the reduction to 3-sat worked was if there's a vertex cover of a certain size, you report true, otherwise you report false. 3-sat isn't something that you can approximate. The answer is yes or no. It's not a number, right? So in principle, there's no way to get an approximation. But even if you were to ask something similar, like how many clauses can I satisfy? Then whether the approximation ratio is preserved depends on the precise details of the reduction. So one thing I can tell you, for example, vertex cover has good approximation algorithms. maximum independent set, which for purposes of proving NP-hard is just, well, the complement of a vertex cover is an independent set. So you solve one, you solve the other. But maximum independent set does not have good approximation algorithms. Right? And in particular, right, so I'm just going to say no here. All right, so maximum independent set is NP-hard to approximate within a factor of big O of n to the 1 minus epsilon for all epsilon. In other words, if I promise you that either, I'm going to give you a graph, and I promise on a stack of Bibles a mile high, this graph has an independent, the largest independent set of this graph is either extremely small, it has n to the 1 over 100 vertices, or it's extremely big, it has n to the 99 over 100 vertices. I just want you to tell me which one of those it is. That problem is NP-hard. You cannot approximate the size of the maximum independent set. There is no useful approximation that you can do. Right? Obviously, you could tell the difference between 5 and n in polynomial time because you just look around. Are there 6 vertices that make up a clique? But that's not useful. Right? You can't tell the difference between n to the 0.00001 and n to the 0.999999. Right? But vertex cover, it turns out, you can approximate within a factor of 2. Okay. I'm going to ask you to guess an approximation algorithm. Let's let somebody else guess. Yeah. Okay, so we'll try to do exactly what we did before. Sort the nodes by decreasing degree, I guess. Right? Okay. And then mark the maximum degree node. Discard that node and its neighbors. V and its neighbors. And then recursively compute a vertex cover of everything else. I mean, this clearly runs in polynomial time. I find the largest degree node by a linear scan. I mark it, then I compute another graph that removes that node and its neighbors, and I recurse on everything else. All right, so this is a greedy thing. This is a log n approximation. This computes a vertex cover that is provably within a factor of big O of log n of the minimum vertex cover of any graph. As often happens when you see log n outside of something that is a divide and conquer algorithm, the approximation ratio is actually the nth harmonic number. Right? In 3 minutes, I don't have time to prove this, so I will do that on Tuesday. But I want to convince you that, and this analysis is typed. I mean, this is exact. I can show the upper bound and the lower bound. I can leave as a homework exercise in a different class. But there's an even easier algorithm. It's the stupidest thing you can think of. Maximum matching actually will give you an exact algorithm if the graph is bipartite. So if I have a bipartite graph and I compute a maximum matching, the vertices that are not in the matching, that number of vertices is exactly the size of the smallest vertex cover. Proof, LP duality, end of proof. So you can compute maximum matchings in non-bipartite graphs in polynomial time, and you can place them some magic to get a vertex cover out of it, but that's a little bit too complicated. I mean, really, really simple. Yeah.
For the independent set, why can't you just approximate the vertex covering before n minus the vertex?
Okay, so the largest independent set has size 10. I approximate the largest independent set. My approximation is say 5. No, sorry, the largest vertex cover has size 10. I compute an approximation 20. Okay, so n minus 20 as an approximation of n minus 10 is pretty good. But if the smallest vertex